Do you ever wonder how ice skaters skate? It is basically because they don't skate on ice, but on water. Because of the pressure, even when the air around is almost freezing, there is still a thin layer of water at the top, caused by the melting. Faria discovered that we could stick 2 blocks of ice if we put one on the top of the other. That's Regelation. So, to simulate the phenomenon, we used a copper wire to make pressure on the ice to see if it would reconnect again or if it would cut in 2 pieces.
First, we'll go through the experimental and visual data, then go through the numbers we got and finish off with our conclusion.
Well, things start off with the wrong foot, but that's science for us. Our first ice subject was a 2-liter bottle, and our goal was to cut through it with a wool line, holding about 3 kilograms.
But what happened was, we spent 3 hours waiting for a cut that didn't happen at all.
Halfway through our day at the lab, we decided to try another piece, and even though it wasn't really a success, it was better than the first.
After the first bottle broke due to the isolated pressure and fast melting, something we will explain later on, we took off the wool line and switched to a copper one, much thinner that would in theory go through easily with 2 kilograms, but again it didn't go as expected.
At the same time, we put an ice cream box ice with the same thin copper wire with 1.4 kilograms and worked much better in less time.
On the first day, we concluded 3 things. Wool is an isolating material. It doesn't conduct energy or heat, so it's much harder for the ice to melt around it, even with the pressure. Second, the piece with thick diameters won't work for a limited time due to the big volume of water they hold frozen. Finally, the ice needs to be in a surface that doesn't affect the experiment, that is, does not heat up or has an uneven surface that the ice and wire's weight will apply pressure upon.
We figured it'd be better to put the wire through the thinnest side, so that the pressure would be more effective.
The piece weighed about 700 grams and was laid sideways, so it could have more stability and still allow the copper wire, this time thicker, to cut through the smaller area available.
This time we had 2 pieces of wood to stabilize and isolate the ice. The one that supported our 6-foot ice had vertical cuts to allow gravity to fully bring the weight down and make the wire cut through the ice.
This time around, the results were much better and clearer. The wire managed to get halfway through the ice. The knots we made to connect the pieces of copper and safely hold the wave got stuck in the wood's cuts, and that's the only reason why it didn't go all the way through.
Nevertheless, it worked. Even with the ice melting due to room temperature and time being exposed, the piece reconnected above the wire's path. At the end of our day at the lab, the wire got stuck in the middle of a still very strong ice.
On this day, we took out a piece as similar as possible to the previous one, also weighed about 700 grams and the same 5 kilograms weight. However, we used an isolated wire with the most same diameter as the copper one.
We cannot even say that it worked throughout 3 hours, because the ice melted and fell down before. However, our results strongly indicate that the phenomenon is related to thermal conductivity of the wires. Because of that, all time spent in the lab only result in a minor slit on the ice surface.
According to the table analyzed, we understood that the time of regelation affected by the wire cut in the block was better reached by wires that have a better thermal conductivity, like copper, and the diameter influenced the area of pressure applied on the ice, showing better results when the diameter is wider, as in 2.36 copper wire.
Throughout the experiments, we concluded that not only the diameter of the wire was important, but also its thermal conductivity was shown to be relevant.
Even though thin wires create more pressure, we weren't able to use them much since they couldn't hold heavy weights. But bigger wires work just as fine because of the bigger mass tied to them.
Strings made of heat-insulating materials such as wool and rubber did not achieve satisfactory results, since it couldn't cut through the ice as well as other materials.
With this, it can be understood that water has an anomalous behavior, since it does not behave thermally like most liquids, something proved by the experiment and which is shown, for example, in ice skating rinks, where the phenomenon is similar to the experiment carried out.